Today is the first day of our Unit 4 Covalent Molecules module. So we're going to go ahead and get started with our first day of covalent. Okay, today we're going to review concepts of ionic naming, and then we're going to compare and contrast of how ionic and covalent are different. So to begin with, let's review a little bit about ionic bonding. In an ionic bond, electrons are transferred from a metal to a nonmetal, or sometimes polyatomic ions may be present. Remember, we can find those on our periodic table in the little box on your periodic table. And in an ionic bond, elements that participate in these types of bonds are called compounds or formula units. Some examples are every single kind of salt, including like table salt that you eat, aluminum chloride, copper 2 nitrate, and sodium chloride. When we name an ionic compound, first we name the metal, which we call the cation, and I told my students to think about the word cat in cation. So metals, I told them metals go meow. That's how we can remember that they're metals. They're the cations. And then we name the nonmetal, the anion, and we change that ending to IDE. When we have polyatomic ions present, we don't change their names when we name them. We leave them alone. And usually we'll write those polyatomic ions inside of parentheses. Remember, however, many transition metals require a Roman numeral to indicate their oxidation number. Can you remember which ones? Here we go. It is most of the periodic table. Most of the periodic table requires a Roman numeral. So all of these, everything in this orange section will need a Roman numeral. Most of the periodic table, all of that, they'll require Roman numerals when we name them. There are a few exceptions in the metals, that is silver, zinc, cadmium, aluminum, gallium, and indium. These have set charges, and then of course everything in the A groups. But all the stuff in orange will need a Roman numeral. All right, so when we name ionic compounds, we're just going to review. We're going to name them. First, we're going to check on the metal and see if there needs to be a Roman numeral. Sodium is in the A group. It's in group 1, so no Roman numeral necessary. So we just write out the metal first, sodium, and then this is chlorine, so we're going to take off the ending and add IDE, so it's going to be sodium chloride. Okay, next one, step 0, always check and see if this is a transition metal. Copper is a transition metal, so that means we are going to need a Roman numeral. So if there's no subscript there's no subscript, then we have to just think backwards. So I'm going to look and think about the oxidation number of oxygen. That is -2. So I know for sure that if this were to crisscross, that -2 would have gone over here. But since there is no subscript over here, that means the copper must be a +2 charge, which would crisscross and then reduce down to the formula that we see. So this is going to be copper 2 oxide. All right, how about this copper? Again, there is no subscript here on the anion. However, when there's nothing there, and in the cation place there is something, we don't have the situation that we just saw above. That means there's an understood 1 here, because I know the charge, this 3 came from the phosphorus. Phosphorus has a -3 charge. So that means this copper must have a +1 charge. So when they crisscross, that 1 would go over here, and the 3 would go over there. So this one is copper 1 phosphide. All right, moving on. Zinc. Remember, our step 0 is, does this need a Roman numeral? Zinc is one of our exceptions. Zinc always has a +2 charge, so we don't need to worry about putting a Roman numeral in the name. So this is zinc bromide. All right, next one. My step 0 is, does it need a Roman numeral? Iron does. It is in our transition metal area. It's in that orange area that we saw on the last slide. So this is going to be, I'm going to look to the anion, and if there's a subscript there, most of the time that's what your Roman numeral is going to be. So that's iron 3 fluoride. Okay. There it is, if in case you couldn't read my terrible handwriting. All right, so we just did naming. Formula writing is, I think, easier than naming. So here is another example. We are going to say, step 1, we're going to change the name to symbol. So aluminum is Al, chlorine is Cl. Aluminum has a set charge because it's in that exception block of +3. Chlorine has a set charge of -1, and they crisscross. So crisscross and jump down. The 3 will come down, and the 1 will come down. There's our crisscross. And then reduce and erase. You don't have to reduce the 1, but realize when you see it written out on tests and answer choices, ones that are subscripts are never really written. So, but I'm not going to count it. I wouldn't count it, say that this is wrong. Just know that on your test or in real life, we just don't write the 1s as subscripts. They are understood to be there. And the last step is reducing. If there is nothing to reduce, I can't reduce a 1 and 3 without making a fraction, don't reduce. All right, so let's practice that. Aluminum, Al, chloride. So we just did this one. So that'll be AlCl3. All right. I'll write that a little more neat. Okay, next one, tin 4 oxide. Tin is Sn. Oxygen is O. This 4 here in the Roman numeral tells me that this tin has a +4 charge. Oxygen always has a -2. So when they crisscross, the 2 will come over here. The 4 will come over here. And then we have to reduce. When we can reduce, you need to reduce. So 2 divided by 2 is 1. 4 divided by 2 is 2. So that will be SnO2. Next one says sodium sulfate, Na. Sulfates, okay? That's when you need to use your polyatomic ion list, okay? So we found that on our periodic tables, and I am going to grab my list. So on your periodic table, it is in the box that says common polyatomic ion list. So sulfates, and you copy it exactly like it says, is SO4 with a -2 charge. And then, of course, my sodium charge is +1. So you just copy it from that list on your table exactly as it appears. Then we do all the other steps like normal. So 2 and 1. We just crisscrossed. Okay, now barium. Step 0, does barium need a Roman numeral? Or is barium a transition metal? No, it is not. So I'm going to change it to symbol, barium. Chlorate, that ATE, and again, ATE ending, that should be getting you thinking polyatomic. Polyatomic. So if we see that ATE or ITE, look at your polyatomic ions list. So I noticed that, so I'm going to copy it just like I see it. I just filled in the barium charge. Oh, and it's actually +2. Barium is a +2. So check on your polyatomic ion list and copy it exactly like you see it. It is ClO3 with a -1 charge. Crisscross. And then that 1. And there we go. All right, so that was a quick review. Again, always be looking for, is there a polyatomic ion? And does this need a Roman numeral when I'm naming? All right, now onto our new stuff. So now we're going to begin talking about covalent bonding. Covalent bonding. Unlike ionic bonds, which occur between a metal and a nonmetal, covalent bonds involve only nonmetals. So there are none of the difficulties that we ran into with ionic bonding, because all of our problems came from what we say metals are messy, the needing Roman numerals or polyatomic ions. Covalent bonding does not have these issues. In a covalent bond, electrons are shared. So in ionic bonds, they were transferred. The metal would give away its electron to the nonmetal, but in covalent bonds, they share electrons. Okay, they're sharing. Some examples are water, carbon dioxide, and hydrogen. These are some very common covalent bonds. Just like in ionic bonding, the reason that these atoms are bonding is to complete their octet. They just are going to share electrons instead of taking them away. But they're still at their basic drive behind bonding is that need to get to a complete octet. There are a couple of exceptions. Hydrogen we've already talked about. Just like before, hydrogen doesn't have room on its first shell because it's very small. So it's only trying to get to 2 valence electrons because that's all that can fit. Boron is just kind of a weirdo. We call it boron the moron. Boron's very weird, and it's only trying to get to 6 valence electrons, not 8. But other than that, everybody else is trying to follow the octet rule. So when 2 or more nonmetals bond, neither is able to lose electrons. Since they can't gain electrons because metals gain electrons, metals lose and then nonmetals will gain. They can't do that here. There's not a way for them to do that that doesn't violate octet rules. Instead, they compromise by sharing their electrons. And as a compound, the elements aren't as energetic and are more stable once they're bound together. So how do you figure out, is it ionic or is it covalent? Metals. Okay, if there's a metal in there, it is definitely not covalent. There are no metals in a covalent bond. So let's see, let's practice. Can we identify ionic versus covalent? Okay, like I said, metals are the key. Really, all you have to do is look at that first one, right? Because we always write metals first. So if you see that that first one is not a metal, it is going to be covalent. Here, this is a metal. That's magnesium. So it is ionic. Cesium. That's a metal. There it is. Okay, so this is, so there is cesium. So this is ionic. This one is covalent, no metals there. Si. That's a little bit tricky, right? Because it's technically a metalloid, but because, remember our line is here, we treat everything to the right as if it is a non-metal. So this gets classified in as a non-metal, even though it's technically a metalloid. So this is covalent. And this last one got a little bit cut off, but that says Mg, right? So this is ionic. Okay, so identifying ionic versus covalent, it says which of the following is not an ionic compound. So your keyword is not. So if it's not an ionic compound, you're looking for a covalent. So let's eliminate metal. So that's ionic. Metal, that's ionic. Metal, that's ionic. So our answer is D. And again, which is not. Okay, so we're looking for a covalent. Cross off. If you see a metal, it's ionic. So it's B. Okay, more practice. Identify as ionic or covalent. Once again, look for the metals. This is a metal, so this is ionic. This is a metal, ionic. Not a metal, covalent. This is a metal, so I wrote M. That's a metal, so it's ionic. This is not a metal, so it is covalent. Silver is a metal, so it is ionic. Sodium is a metal, so it is ionic. Nitrogen is not a metal, it is covalent. Ionic versus covalent versus metallic. So when we're trying to decide what type of bond it is, first you want to think about what kinds of elements are in there, what do they do with their electrons, and when can they conduct electricity. And this is a lot of words, but we'll go through it. First part's review. Ionic bonds or compounds are made of metals, one metal, one non-metal, and electrons or polyatomics, right? But the key is there's a metal in there, one of each, a metal and a non-metal. Electrons are transferred. One electron is lost. The metal lose their electrons. The non-metal will gain. And they have high boiling points and melting points. They also are good insulators only when they're in the aqueous or melted state. Okay, so if they're in water, they'll form crystalline solids. Think about like in caves, like the crystals you'll see. They're often called salts, even if it's not table salts, we'll call them salts. They're almost always able to dissolve in water, and one particle is called a formula unit or a compound. On the other hand, covalent bonds are only nonmetals. This is the biggest way to tell. They are only nonmetals. Here, The electrons are shared. Shared. We say for covalent, sharing is caring. They have low boiling points and low melting points. So basically the opposite. And they are always insulators. Ionic bonds are insulators when they're in solution, but covalent bonds are always insulators. They do not conduct electricity. And many will not dissolve in water. And unlike ionic, where they were called formula units, these are called molecules. And the last one, a new one, bonding type that we haven't talked about yet, is called metallic bonds. And what you think is true, these are made only of metals, hence the name metallic bonds. So covalent is only nonmetals, metallic bonds are only metals. And here, what happens with the electrons? The electrons are delocalized, meaning there's like a sea of electrons that's shared by all the atoms. They have high melting points and high boiling points, and they are easily reshaped. These are all properties of metals. They're malleable and ductile. The delocalized electrons provide high electrical conductivity when they are solid or melted. So, you know these are just properties of metals. They're great conductors. And they are insoluble. So if you put a piece of like tin foil, like aluminum foil, in water, it's not going to dissolve. Okay, so take a minute and compare, contrast. Let's write. Okay, ionic bonds. What kinds of elements? Metals plus non-metal. One of each. What do they do with their electrons? They transfer them. So the metal will give away its electron to the non-metal. When can they conduct electricity? When they are in solution. For a covalent bond, what kind of elements are they? It's a non-metal with non-metals. Only non-metals. What do they do with their electrons? They share. Sharing is caring. Can they conduct electricity? No. Nope. When can they conduct electricity? They don't. Not good conductors. Never. They never conduct. In metallic bonds, it is a bond with metals only. So metals only. What do they do with their electrons? They're in their sea of electrons. Why is this all stuck? I don't know why it's doing this. Here. There we go. Sea of electrons. And that last one got a little bit cut off. Sea of electrons. Okay, but it says when can they conduct electricity? Always. They're good conductors. Always. Okay. So this is like just a slide that will get you thinking for next time. So we'll leave with that and we'll head to our homework tutorial.